Dear friends, I am Dr. Gaurav Singh from Sagar University, Dr. Hari Singh Gaur Vishwavidyalaya Sagar from the Department of Applied Geology, and I will discuss with you today the principles of stratigraphy. Stratigraphy is the branch of geology that deals with the formation, composition, sequence and correlation of the stratified rocks. Since the whole earth is stratified, at least in a broad sense, bodies of all the different types of the rocks, igneous, sedimentary, metamorphic, are subjected to stratigraphical study and analysis. In most cases, however, stratigraphy focuses on the evaluation of sedimentary rock strata. Modern principles of the stratigraphic analysis were developed in the 18th and 19th centuries by geologists such as the Niels Stinson, James Hutton, Georges Cuvier, William Smith and Charles Lyell. By 1900, all the intellectual tools needed for the description, sequence and correlation of the strata were in place. Shortly after 1900, the tools needed to establish the absolute age of the minerals and containing unstable radioisotopes also became available, giving stratigraphers a physical basis for making chronostratigraphic correlations, at least in certain favorable stratigraphic situations. Since the 1950s, efforts have been made to establish international standards for stratigraphic nomenclature and the usage of the stratigraphic terms and internationally agreed designation of the type sections or stratotypes for various sorts of the stratigraphic units, especially those related to the chronostratigraphy. Then coming to the stratigraphy, and the stratigraphy is the science of strata, which are a common feature of many landscapes constituted mainly by sedimentary rocks. However, strata hereafter beds are also present, although strongly deformed tectonically in metamorphic rocks which were sedimentary in origin, and in volcanic rocks, wedge-shaped, channeled, lenticular and irregular stratified sediment bodies are commonly found, but beds usually are tabular or laminar volumes of the rocks bounded by flat and laterally continuous stratification, that is bedding surfaces. Bedded sedimentary rocks are the obvious results of the erosion, transportation and deposition, especially when they are terrigenous clastic in origin, but also when they are derived from the chemical precipitations as well, from organic matter accumulation or from the interplay between the volcanism and sedimentation. Beds actually represent units of the sedimentation and pieces of the geological time during which a net sedimentation was locally produced in a restraint area that had been affected by the past by active geological processes. The stratigraphic record and its significance is something that we are going to discuss shortly. Beds can appear isolated, but more commonly they form the stratigraphic successions up to several thousands of meters thick, which are sediment fill of wide ancient sedimentary basins. These are the crustal depressions mainly generated by large scale plate tectonic processes in which many different sedimentary environments can be present. Generally, continental, marine and transitional sedimentary systems are distinguished, and each of them can be erosional, equilibrial or depositional. The dynamics of these systems produces a stratigraphic record in which sharp to gradual changes between the successive sedimentary beds or the groups of the beds, stratigraphic units can be observed. However, many bedding surfaces may actually represent erosion or no sedimentation. These stratigraphic units are characterized by their position and arrangement within the stratigraphic column, and especially by the nature and lateral and vertical organization of their facies, that is, their lithological, petrographical, mineralogical and or chemical composition, their texture, grain size, shape, relationships and other physical properties such as the remnant, magnetism or many others, their fossil content and their geometrical features such as sedimentary and post sedimentary structures or stratigraphic architecture depending upon the scale of observation. The nature, distribution, dynamics and evolution along geological time of the different sedimentary systems present within the basin and of the stratigraphic depositional units are bounding surfaces that they produce depends on parameters such as the general shape and topography of the basin and the adjoining areas, nature of and distances to the sediment source, drainage pattern, current system, base level, usually the sea level, position and stability and the organisms living on them. These parameters are essentially controlled by climate, tectonics and evolution of life. So, stratigraphic succession of the sedimentary basins actually contains an what you call as the ordered information in space and time about. Now, we will discuss the past distribution of sedimentary systems and the environments within the basins and surrounding areas and their dynamics, that is paleogeography. Second is the temporal succession of the climatically, tectonically, which is controlled by the geological processes, which you call as the paleogeodynamics, paleotectonics, paleoclimatology, paleooceanography, etc., either acting gradually or suddenly events and thus producing progressive to very rapid or sharp changes in the rock record. Then comes the evolution of life and of evolutionary processes in the marine and naturally the terrestrial biosphere or the paleobiology. By applying simple rules or principles of stratigraphy to the description and interpretation of stratigraphic succession, it is possible first to subdivide and organize the local stratigraphic column in superimposed stratigraphic units or rock units separated from each other by bounding surfaces, what you call as lithostratigraphy. Then to reconstruct a relative dating scheme for successions gradually changing or sudden geological events like event stratigraphy recorded for each local stratigraphic column either by the means of fossils, that is biostratigraphy, remnant magnetism or the magnetostratigraphy, volcanic ash ejections, that is tephrostratigraphy, paleosols, that is pedostratigraphy, chemical properties of sediments, that is chemostratigraphy, and isotope stratigraphy, cyclic evolution of the strata called as cyclostratigraphic succession of depositional sequence, that is sequence stratigraphy, and their bounding unconformities like allostratigraphy, indicators of the climate change, that is climatostratigraphy, or by the combinations of several of these criteria. These producers or these procedures allow the establishing solid time stratigraphic schemes, that is chronostratigraphy or relative geochronology for the study successions. Then is to propose correlation, that is comparison in space and time between the stratigraphic successions of different sedimentary basins. Then to interpret the dynamics and paleogeographical significance of the studied record at different scales of the observation from individual beds, that is stratonomic analysis, or group of the beds, that is facies to sequence analysis, to the basinal scales, that is basin analysis, or even to global scale if the observed phenomena are recognized worldwide. And to reconstruct the geological history of the earth in different areas of the world and to recognize the variation in space and time since the origin of Earth's crust up to the present. By consequence, the stratigraphic record is something like a complex, fragmentary and partially destroyed book, in the pages of which are the strata and geological history of the earth was written. By correlation of the local stratigraphic succession with the standardized reference sections, it has been possible mainly during the 19th century to develop a geological time scale composed of the standard stratigraphic divisions. As such, the units of the chronostratigraphy refer to the physical rock units mineralized by the stratotype and all the correlated successions, erradium, system, series and stages, whereas the geochronology refers to the time of the same units represented as eras, periods, epochs and ages. The absolute time calibration of the chronostratigraphic or geochronologic unit is based mainly on the radioactive decay of the elements contained within the magmatic rocks present in the stratigraphic succession. However, it is obvious that both disciplines are different aspects of the same work or the time correlation of the rock units. The principles of stratigraphy is something which we are going to discuss. It is the relative chronology and the sedimentary dynamics. The above mentioned principles which we have discussed so far, it cannot be considered as laws, but as the methodological, the statements that sustain stratigraphical reasoning by the synthesizing a lot of observed geological phenomena and that are justified by the statistical means of the consequence. The proposal of a relative geochronological scheme for a local stratigraphic column is primarily based on the following principles, each one of which is briefly stated here, and these are as follows. Like the principle of superposition, lower beds within a stratigraphic succession are older in age except if the succession was tectonically overturned and was reversed. Then is the principle of original horizontality. The beds in the sedimentary basins were originally horizontal or nearly horizontal if not disturbed. Then comes the principle of incorporated fragments or the rock fragments within the beds, necessarily which are older than the bed itself, and the principle of cross-cutting relationship. That means a disrupted pattern is older than the cause of the disruption. So, one bed or one set of beds unconfirmably cross-cutting another rock pattern, either magmatic or tectonic surfaces or layer cake successions of the sedimentary rocks, is younger than the later. However, the observation of the stratigraphic architecture of many sedimentary basins at all scales by means of the direct and indirect methods, in particular by the seismic methods, demonstrates that the rock record does not always simply corresponds to the layer cake model of more or less parallel, laterally continuous and originally sub-horizontal beds bounded by sharp surfaces and generated by aggradation or vertical sedimentation. On the contrary, observed or deduced geological relationship in many stratigraphic succession demonstrates that the beds originally deposited with dips something like 30 or more are quite frequent, especially in continental margin deposits. Lateral facies changes are ubiquitous at all scales. Lateral accretion and progradation are quite common styles of the formation of small and large sediment bodies, and the stratigraphic units are frequently wedge shaped. Then the modern approach of the sequence stratigraphy in fact has given full consideration to these geometrical relationship and has developed a more complex way of subdivision of rock units based on the recognition of unconformities. Nevertheless, these facts do not invalidate the classic principle of superposition itself that remains the fundamental methodological tool for constructing a local relative chronological classification of the rock record. In addition, the local relative geochronological, that is chronostratigraphical schemes, can laterally be extended and interpreted in terms of the sedimentary dynamics that is generated in them. That is, in terms of the successive or the physiochemical processes acting in a sedimentary system within an ancient sedimentary basin and changing in space and time by applying the following stratigraphical principles. First is the principle of physical continuity. Beds along their margins of the sedimentation area, which was a former depositional system which is now frozen in terms of the stratified rocks. Then comes the principle of faunal or the paleontological succession, which states that the beds deposited at the same age in different sites but under similar environmental conditions have the same fossil association, and which is the basis for the biostratigraphy. Then is the principle of uniformity, which affirms that the geological processes operating at present are similar to those operating in the geological past, or briefly, the present is the key to the past. And the principle of facies correlation or Walther's law, which affirms that the sedimentary environments and the facies formed beside each other in the space can appear superimposed on each other in the stratigraphical succession. All these principles allow the correct description and interpretation of the local sedimentary successions in particular and that of the stratigraphic record in general. It is important to remind that by applying the uniformity or uniformitarian methods, the nonetheless possible to reach the catastrophic conclusions like actualistic neocatastrophism. Event and cyclostratigraphy and relative geochronology is something we will be discussing. By applying the principle of physical continuity and paleontological succession, it is sometimes possible to identify and define guide or horizons which are single beds or narrow sets of the beds of a different lithology or fossil content to that of adjoining beds, which can be recognized widely and which by consequence are very useful for the physical correlation between the different stratigraphic successions. Actually, these two principles are a particular expression applied to the genesis of the individual environmental layers or to the biological evolution as recorded by the fossils of a more general statement called as the principle of simultaneity of events. According to this, many sudden natural phenomena that affected wide regions, if not the whole of the world, can be considered as the geologically instantaneous and can be physically detected in the rock record either as the single beds or as a particular group of beds or as the zones of rapid change in different physical, chemical or paleontological features by a constraint in the rock record. By the consequence, their effects in the stratigraphic succession can be used for the relative time correlation and relative geochronological classification. If such events are sporadic, unique and catastrophic, they produce either discontinuity surfaces or lithologically peculiar single event beds that generally are very easy to be recognized either by the direct observation in the field or by the means of the analytical work in the laboratory or by the rock sampling. But in other cases, such events are episodically or if not rhythmically recurrent and produce a more or less continuous and repetitive record. Thus, this record can be formed by the stacked individual sediment beds that can be physically traced from one part to the another, or by gradually changing sediment properties that in some cases oxygen isotope record, for example, can be standardized for local to global correlation. Examples of sporadic events or sporadic beds or horizons are among others. Then unconformities either tectonically or eustatically generated. The tephras, ash layers produced by explosive volcanic events, single turbidite beds or mass flow deposits generated by the sediment gravity flows either climatically or tectonically induced seismites if due to the seismic shocks. Tempestite beds, graded deposits resulting from the storms. Ice rafted detrital beds between the deep marine sediments generated by the catastrophic melting of the large part of the ice sheets and ice shelves, such as the new Henrich layers and of the North Atlantic during the late Pleistocene. Clay horizons rich in organic materials such as those produced during the Jurassic and Cretaceous oceanic anoxia events, that is OAEs, or as Pleistocene Mediterranean saprophyls. Iridium rich layers such as that found at the Cretaceous Tertiary or KT boundary that are interpreted as produced by meteoritic impact. Condensation beds generated during the cycles of sea level rise and fall are changes in the ocean biogenic productivity which produces laterally continuous glauconitic, phosphatic or ironstone rich horizons within the pelagic successions, or widespread Paleogene to Miocene deep water hiatuses found in the oceans that are interpreted as due to global paleoceanographic revolution. Examples of the recurrent indications of the episodic events that produce a more or less continuous and repetitive rhythmic or not record are, for example, are the polarity geomagnetic reversals and other magnetostratigraphic signals, that is magnetic susceptibility, as well as many indicators of the sudden climatically or oceanographically induced changes as shocked or the stacked turbidites, tempestites or other types of lithologically recurrent beds, limestones and marls, radiolarian cherts, etc. form thick rhythmic succession. Warped lacustrine succession, the vertical changes in clay mineralogy, tree ring records, which is dendrochronoclimatology, laminated speleothems, cave centers, stalactites, stalagmites and the flowstones, windblow deposits due to continental scale desert storms such as those that produce loessous successions during the Plio-Quaternary glacial periods, and associated paleozols developed during the interglacials, curves obtained from the quantitative micropaleontological analysis in marine to continental records from the pollen, that is palynology, foraminifers, diatoms and many other fossils. Chemostratigraphic continuous records of the isotopic or not, either obtained in deep sea cores or in pelagic successions exposed in the continent or in ice cores from the continental ice sheets. As many of these rhythmic sedimentary records are being increasingly demonstrated to be controlled by the regional or global climatic or eustatic sea levels changes. They represent one of the fundamental target of modern geological research, that is the cyclostratigraphy. Among the most important cyclostratigraphic or chemostratigraphic record for the chronoclimatic significance and its very precise and extremely fine time resolution, the marine oxygen isotope record must be specifically mentioned. It is mainly based on the very slight systematic O18 to O16 ratios, variations with age shown by the foraminifera calcareous test of the sediments drilled in all the oceans. They reflect the changes in the isotopic variation of the ocean waters driven by the periodic accumulation and melting of ice in the northern hemisphere during the late Pleistocene. This regularly evidenced for the first time by the Cesare Emiliani in 1955. Has been proven to be in phase with the periodic variations of the orbital parameters of the Earth's evolution calculated by Milutin Milankovitch around 1930. Although many other isotopic records are increasingly used either in the marine cores or in the ice cores, the time resolution for the oxygen isotope curves obtained for the last 2.5 million years from now is much higher than that of the any other indicators. In fact, changes in the other oxygen isotope record are very rapid and virtually synchronous of globally scaled, and indeed a very precise time calibration has been obtained for the different parts of the isotopes curve by the orbital tuning, that is, by its correlation with the insolation curves obtained by applying to the Milankovitch's astronomical theory or climate change, especially for the middle and late part of the Quaternary. This makes the isotope stratigraphy the finest relative dating techniques based in the stratigraphic correlation. In conclusion, stratigraphy and relative chronology or the geochronology today are increasingly analytical and progressively more synthetical geological sciences now, and more sophisticated methods are being introduced to describe better and finer the rock record, to reach the higher spatial and temporal resolution, and to build a progressively more detailed geological timescale. This allows more and more precise correlation between the different stratigraphic successions by means of event stratigraphy, and thus provides a more detailed picture of the geological history of the Earth. Thank you very much.